Hey guys, welcome to lesson 6 in unit 9 for acids and bases. We're going to talk about Bronsted Lowry bases and describe this is a different theory. We're going to describe how it connects to the other theories. All right, let's go ahead and start our notes. The alternate acid base theory. So like I said, this is called the Bronsted Lowry, named after the two scientists who made it. All right, not bad. Bronsted Lowry theory. This theory explains the behavior of weak acids and bases. So we talked a lot about strong acids and bases, and now we're going to learn a little bit about weak acids and bases. Weak acids and weak bases. Those are the ones that don't disassociate 100%. That's what makes them a little different than strong acids and bases. Definitions of the theory. Basically, it's built around the idea of being proton donors and acceptors. Okay, let's get deeper into the definition. Bronsted Lowry the theory is that you have acids are the proton donors. And so not much with that. That means whichever compound gives up a hydrogen plus ion. So let's take a look at this sort of poor graphic. We have HCl over here, if you can't tell. Oh, HCl, guys. And then we have H2O. And I'd like you to sort of connect the idea that one of the hydrogen is dissociated from the hydrochlorine and then attaches here. So hydrochloric acid definitely acts as a Bronsted acid. It will work for weak bases too, but we'll talk about that later. And what we end up with, of course, is H3O over here, and we end up with a chlorine ion. All right, a Bronsted-Lowry base is described as a proton acceptor. So whichever compound takes up a hydrogen. Also known as a proton. All right, so we got ammonia and water, and you'll notice that the water gives up a hydrogen and the ammonium is formed and you have the OH formed. So who accepted the hydrogen? This will be our Bronsted-Lowry base because it accepted the proton. There brings up a connection between all of these things. They're called conjugates or partners. So we'll use two brackets connecting one side of the reaction to the other. So when I see like hydrochloric acid, you'll see it's connected to the chloride ion because it's the process of giving up hydrogen. So this is what we call the acid, and this is what we'll call a conjugate base. Now, the reason it's a conjugate is because it's connected to the hydrochloric acid. You see the chlorine in both sides. It's a base because it would accept a hydrogen if it could, but during this process, the left to right reaction shows that hydrochloric acid acts as an acid, and the conjugate base acts as a base. H2O, though, water in this case acts as a base because it accepts a hydrogen, and so H3O that's formed is called a conjugate acid. And this is the acid-base conjugate pairs. Within the pairs, they differ from each other by merely one hydrogen, so that's the thing that's connected. How do I know? For example, to connect the line between hydrochloric acid and chlorine? Because the only difference between the two is exactly one hydrogen. And the same thing, of course, goes here. What makes this different than this is one hydrogen. Okay, good, it just goes temporarily. Okay, notice the acid always has one more hydrogen than the base when you're looking on the left. And here's the key to those words. All right, let's move on to some more questions to practice this. Use brackets just like we did before. So I'm going to look at these and I'm going to figure out which ones differ by just one hydrogen. And the ones that do, we have this one and this one. They both are just different by one hydrogen, so I'm going to connect them. And I'm going to connect the water and the OH because it's different by one hydrogen. And then I have to decide which one of these lose a hydrogen and which one of these gain a hydrogen. This one loses a hydrogen, so it's called an acid because anything that donates a proton, and therefore it's connected to a conjugate base. This one is a base because it gains a hydrogen, and therefore it's connected to a conjugate acid. All right, that's all we have to do for that one. Let's look at the second one, and go ahead and try it on your own. Connect the two that connect. I'll go ahead and do it with you. You can pause the video if you want to try these on your own. But I'm going to say hydrogen and the chloride ion, hydrochloric acid and the chlorine ion. And I notice that hydrochloric acid is an acid, and this makes this a conjugate base. This one must take up a hydrogen, so it's a base, and it must be connected to a conjugate acid. All right, take a look at this one. I think you can identify that as an acid, therefore it connects it to a conjugate base. We got this water acting like a base connected to a conjugate acid. This one, a little trickier, they both have hydrogens, but one of these loses a hydrogen, and it's nitric acid. So that's our acid, and this is our base. This is then therefore our base, and this is our conjugate acid. Oh, I forgot to call this a conjugate base, sorry. All right, and then there are also substances called amphoteric and amphiprotic. I'm going to go down there. This is a substance that can act like an acid or a base. So by Bronsted-Lowry's definition, it can be a proton donor or a proton acceptor. For example, water, we noticed in the above examples, can both be an acid or a base. So if we look at this reaction, when you just have water sitting there, something weird happens. And it balances out, but we do have hydronium ions and we do hydroxide ions. And in fact, there's 10 to the negative 7 moles of both of these present in water. And let me just explain this one more time. We look at the water, we connect it to either one, it doesn't matter which one, because they're both identical on the left. But on the right, we have to realize this water molecule is gaining a proton, so it's a proton acceptor, so it's a base. And that means this must make it a conjugate acid. And if that particular water molecule was a base, this one must act as an acid because it donated a proton, which means it's connected to a conjugate base. Now, amphoteric substance must have at least one hydrogen in the formula, which hopefully makes sense. Which of the following substances could be amphoteric? We have H2SO3, HBr, HSO3, and Br. Well, first thing, can't be this one because it has no hydrogen, so it can't be an acid. It has to be able to be an acid or a base. Now, this one definitely can be an acid, and this one definitely can be an acid, and this one can be an acid. But you'll notice something special about this one. There actually is a way for this to accept it, so it could be an acid or a base. I'll show you both. If it acts as a base, it's going to follow the bottom line. A base accepts a hydrogen and it would become H2SO4. How do we know this compound exists? Because you see this negative sign, it means it can accept a proton or a hydrogen. Same thing. And then if it acts as an acid, it could create SO4. Now, I should have said SO3 negative 2. Let me just change that. Sorry, I'm just trying to figure this out. There we go. That's enough. All right, so this would become SO negative, SO3 negative 2. And because it does have a hydrogen to give, and it has a hydrogen to accept. This one can't accept any more hydrogens. This is sulfuric acid. And this can't accept any more hydrogen and be stable. So it is option C. All right, and that concludes our notes. I will open up the practice packet too, so if you want to stick around to do some of the practice problems. The practice packet homework today is 14 to 16. So let's turn to 14 and 16. All right, too far. All right, let's zoom in here. I think it's going to be similar to what we've done before. Let me just zoom in. Okay. In the following equations, draw brackets, okay, between conjugate acid-base pairs. Acid-base pairs, label each, is it acid or base, and explain the question, to answer the question. According to what does H3O act as? So first of all, I'm going to connect these two, and I'm going to connect things that differ by one hydrogen. So now I've connected them. Now I'm going to label them. In the process of H3O to H2O, it gave up a hydrogen, so it's a hydrogen donor. So this acts as an acid, and that means H2O is a conjugate base. This must mean that the CH3COO must act as a base, and that this is a conjugate acid. So we've labeled it. And what does H3O act as? H3O is labeled here as an acid. So in this case, H3O is an acid. All right, let's do one that's a little harder down here. According to Bronsted, Lowry, what does CN act as? Well, let's connect them by one hydrogen. These are all the same compounds, just differing by one hydrogen. You'll notice CN becomes HCN, so it's an acceptor. That's called a Bronsted base. H2O is a donor, so that's an acid. In both, the base is connected to conjugate acids, and acids are connected to conjugate bases. What does CN negative act as? It acts as a base. All right, so that's that page. Let's move down. Challenge problems. And let's do this one. This one looks really complicated. Number 9. We have HCl, connect them. Oh, that's time. Anyway, this acts as an acid, conjugate base. This is a base. This is a conjugate acid. And what does aluminum, blah, 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 act as aluminum hydroxide, sorry. It acts as a base. Okay, you can try these if you'd like. Not very, I shouldn't say not very hard. Go and try them. HCl to NaCl, NaOH. So, is anything acting as an acid? And the idea is that hydrogen is donating and getting rid, and NaOH has accepted it. So this is our acid, and this is acting as a base. But we probably know that already because it's an acid and a base already. But they are connected to conjugate bases and conjugate acids. And water can be an acid or a base, just to recall. All right, that concludes our notes. Thanks for learning.